tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world.
All right. Good evening, everyone, and welcome to this month's Science in the Mountain lecture series. My name is Jackie Belfontaine, and I am the School Programs Coordinator for the Mount Washington Observatory. I'm taking over this month as host for our Director of Education, Brian Fitzgerald. And we have a fantastic speaker here with us tonight. So we have Brian Campbell here with us from NASA. He is the NASA Senior Earth Science Specialist. And today he's going to be talking about NASA's Ice, Cloud, and Land Elevation Satellite-2 program, also known as ICESat-2. All right, thank you everybody for joining us this evening. For those of you who might be first timers or unfamiliar with our work at the Mount Washington Observatory, we are a private, nonprofit, member support organization whose mission is to advance our understanding of the forces that drive both Earth's weather and climate. So today we have I'm going to get to my poll here in a second, but before we get into that, we have a little bit of a Q&A session we'll be doing at the end of our presentation here. If you're joining us through Zoom, if you look down at the bottom of your screen, you'll see a Q&A function. We'll be collecting questions throughout the entirety of this presentation. And like I said, towards the end, we will be able to look at those questions for our speaker here. But before we get into that, I'm going to quickly launch a poll. Have a pop quiz for you guys. All right, I'll give you about a minute or so to answer this. You should see this popping up on your screen right now. So first we have, where are you joining us from? Second is, have you signed up for this year's Seek the Peak on July 20th, the Mount Washington Observatory's largest fundraiser and our hike-a-thon? And then we have a few questions related to tonight's program. So how many photons on average are there in one single laser shot from the ICESat-2 mission? The NASA ICESat-2 mission measures the height of what? How many countries are a part of the NASA GLOBE program? And finally, how many solar panels does ICESat-2 have? All right, give you guys a little bit more time there. All right, awesome. Seen a lot of answers coming in, and it looks like majority of our friends here tonight are joining us from the Northeast, but we're all over. I see some from the Southeast, Midwest, West, and even outside of the United States. So thank you so much, everybody. And then our second question, have you signed up for Seek the Peak this year? So I see some people have. Some people want to know what Seek the Peak is. A majority who are with us tonight have not signed up yet. Well, that's okay. Towards the end of our program here, I'll tell you guys all about Seek the Peak and what a wonderful event it is to help support the Mount Washington Observatory. All right, fantastic. So I'm going to end the poll there. And with that, thank you all once again for joining us for this month's Science in the Mountains. And I'd love to welcome our speaker. So Brian, are you able to hear me okay?
I can, Jackie. How are you tonight?
Doing wonderful. Thank you so much for joining us. And with that, I'm going to pass the torch to you and let's learn about ICESat-2.
All right, sounds good. And Jackie, how's that look on your end?
It's looking good.
All right, perfect. So thank you, Jackie, for the introduction. And I won't have to go through it. There's a bunch of stuff on there about me. But I just want to tell you, I'm in my 24th year at NASA, and I've been working in the earth sciences the entire time. And just previous to that, I was actually right out of graduate school. I taught ninth grade and 12th grade science, Earth and space science in ninth grade, and 12th grade physics. So, and I've been at NASA since 2001. So today, as you saw, and why you joined, hopefully, is that you saw this is the Science in the Mountain series, and this is a special one with NASA, Photons with a Mission, NASA's Ice, Cloud, and Land Elevation Satellite-2, or ICESat-2. So there's a lot going on this introductory image, but what you're looking at right there, and we'll get more into that further into the presentation, into the lecture, is that those dots you see are actually laser photons. It was you had a question about that in the poll about photons, and each one of those dots that you see is a photon that came from a laser pulse, and it is measuring the height of something. And as you can see here, this image in the background, that is on Mount Washington. So the ICESat-2 satellite hits that location frequently. The ICESat-2 satellite travels very quickly around the Earth at what's called an 88-degree orbit. So it goes around 88 degrees north, 88 degrees south, and it hits the same spot on the Earth every 91 days. So we get observations like this every 91 days. And I'll show you what these observations actually look like when we process them, because this doesn't explain much. It just shows you nice colorful lines over a green Earth background. So not much going on here that you can really discern yet. But hopefully by the end of this, you'll be able to figure out. But before we go specifically into ICESat-2, I want to go into a couple things. There's just one cool image that I found of a location at Mount Washington with Mount Adams next to it. But what I want to do is I want to go through a little bit about, ICESat-2 is part of NASA's Earth Observing Mission Fleet. And this Earth Observing Mission Fleet is about 33 Earth observing satellites from NASA that are in space, rotating around the Earth now, but they are taking observations of different things on the planet, everything from vegetation to clouds in the atmosphere, to looking at the atmospheric chemistry, to looking at soil moisture, to ice, to snow, to the carbon in our atmosphere and the oceans and what's in the oceans, from phytoplankton to, harmful algal blooms and everything like that. So each one of these satellites I like to call a piece of a jigsaw puzzle that helps us understand how our planet is responding to a changing climate. So the first one I'm going to show you here, there's no sound to this video, but it's one of my favorites, and we call this the breath of the Earth. And you'll be able to see this. You're gonna focus on the green and the white. The white is going to be like snow and ice, because you see it in the northern areas. And you see, of course, in Antarctica down there. But then also the greens. The green is going to be vegetation. And at the top left where it says vegetation index, you're going to see the dates changing. The date will be increasing. And what I want you to look at is the fluctuations that you see from north to south, south to north, north to south, south to north. And these are the seasonal changes where we see what's called green up and green down. Okay, green up, of course, in the springtime, and green down at the end of the fall as you're heading into winter. So this is one of my favorites. So I want to show you this here. Here you go. So as you can see, this is really dramatic, and you can see how the date's changing pretty quickly. So this is not from ICESat-2. This is from a satellite called Terra, and the instrument is a spectrometer called MODIS. And what you're looking at here, once again, you're looking at the changing of seasons, and the greenings. But what is really hard to see and is very subtle, you have to zoom in a little bit, is you're seeing the green every year kind of creep up a little further into the northern latitudes, into the Arctic area. And you're seeing less and less. If you look at Greenland, for instance, you can see, you don't expect to see much green in Greenland. But if you look at I'm gonna do that again for a second here, just so you can see this again. But if you look at Greenland, you can see the southern area and the western southern portion and the eastern southern portion. You can see there's a little bit of greening going on there. Also on Iceland as well. But this is one thing we see that's changing pretty dramatically as we're seeing this greening moving further and further north and having less and less ice into, going further into the winter season. So we're basically seeing what's called, this ice minimum and ice maximum changing. The minimum is getting smaller, and the minimum would be towards the end of summer, and the ice maximum would be towards the end of winter once we had a lot of cold months. But we're seeing that is actually short as well. So with that said, what are all these missions that we have up in space right now? And you can see up at the top, there's ICESat-2, which we're going to talk about in detail later. But you can see this is NASA's Earth observing fleet. And when I said 30, okay, those are ones that are flying in space right now. There's definitely more than 30 on this graphic here. But as you start with the one in the middle, the Landsat-7, that's basically one of the older satellites that is still active and working in space right now, taking amazing land cover and land change imagery. So it's also looking at change over time. That's one of the huge things we do at NASA, is that we use this satellite data to, one, look at how things are changing over time, and two, using that information to create prediction models of how things are going to change in the future. So the ones that you see that are in blue, these are missions that are out there now. These are what are called extended operations. So they are working past their original lifespan that we thought that they were designed to do. All NASA Earth observing missions now have a minimum requirement of being in space for 5 years. Okay, all of those have been up there longer than that. You can see the last blue in there is ICESat-2. That has been up since September 15th, 2018. So it's going on 6 years in a few months. And then you have the green ones here. These are ones that are the newest satellites that are in space right now. And then the orange are implementation. So the engineers are building these. Actually, the PACE one there, sorry, the PACE one was the last one to go up. This graphic is because this PACE only went up about a month or so ago. So this orange PACE one should be green. That is looking at phytoplankton and ocean color and aerosols. And then all the way through the yellow ones, that means they are just being talked about right now, and the scientists are deciding what they want to do with these missions. So, when they're in space, they look like this. And I often get the question, it's an amusing question, that do these satellites ever hit each other because they look so close? Well, in the graphic, they do. But, we have them in their specific orbit. So, no, they do not move into each other, crash into each other. But this is kind of what you'd see if you'd be looking at this, in kind of real time and being able to see all the satellites if you were at this perspective. So you see all these different missions moving around here. So the data that comes from all those missions that you saw on this graphic, okay, we get data like this. And these are some of the most important ones that NASA studies. They're the most important ones when we're talking about how we look at climate changing over time. We have sea surface currents. We have what's called a blue marble. So it's looking, you can see there's vegetation. You can see the different things in the ocean. We have the biosphere, so living things again. We have phytoplankton and the trees and vegetation on land. Soil moisture on land and salinity. We have precipitation, of course. We have clouds, which have to do with our weather and long-term climate, precipitable water, and then we have winds. So this is what's called slices, but this is one of a way that we can visualize all the different data that's coming in from the different Earth observing satellites at NASA. So with that said, I'm going to jump into ICESat-2. As I mentioned, ICESat-2, the Ice Cloud and Land Elevation Satellite 2, is a mission that was launched on September 15, 2018 from the Vandenberg Air Force Base, now called the Vandenberg Space Force Base, on the central coast of California, right outside Lompoc, California. If you've ever been there, it's a beautiful location, beautiful place where, the mountains meet the sea. So it's a beautiful place. So ICESat-2 measures the height of objects on Earth. So because it's ICESat-2, its primary objective is to look at how fast the ice is melting in the Arctic and Antarctic. We have two major types of ices. At the North Pole, we have frozen saltwater or sea ice. A lot of people think that it's land at the North Pole, but it's not. It is just frozen salt water or ocean water. At the South Pole, we have land ice or an ice sheet called Antarctica. This ice sheet is surrounded by Antarctic sea ice. So we have the land ice and the sea ice. We have two ice sheets on the planet. One, as I just mentioned, is Antarctica. The other one is Greenland. Okay. Now, what that means is those are covered for the majority of the year, just about the entire year, with lots of heavy snow and ice that's heavily insulated, and it gets very cold in the central parts of it, where we don't get much melt in the central portions of these two ice sheets. But we do see a lot of melt on the outside of it. So when I say outside, I mean the edges, the north, south, east, and west edges of it, towards the edge of these ice sheets. And when that ice melts, that runs into the ocean and increases sea level. ICESat-2 is also able to see the changes in the surface height of the oceans. So it's able to see how fast that ice is melting and also how fast those seas are rising. Then also, think of it this way. When we have sea ice is frozen water. And as you know, when you have, for instance, if you have a glass of water that is filled to the top and you drop ice cubes in it, it's going to overflow. Okay. But if you have a glass of water with the ice cubes that are in it already, when that ice melts, that volume is already displaced, so it's not going to overflow. That's what happens with sea ice. But sea ice does contribute to climate change because the sea ice has a high albedo or reflectivity because it's a white surface. So a lot of the sun's energy that hits the white surface bounces off into space. Some of it does heat up the ice and melt it. Okay, the warmer the climate gets, temperatures get, the faster that ice is going to melt. Well, when that sea ice is gone, where does that energy go from the sun? That energy goes into the oceans. So then we have issues with warming up the water of the ocean, melting the ice around it, and then when we heat up that water, when we warm that water, we get expansion. So then we get sea level rise as well. So it's kind of a bad situation either direction. So ICESat-2 is able to measure these small variables, and you'll hear this in a video I'm going to play in a second. But ICESat-2 is very precise. ICESat-2 can see changes in the height of ice as small as 2 centimeters. So if ICESat-2 hits a portion of southern tip of Greenland, and then it comes back basically 91 days later, 3 months later, and sees that change, and if it's like a 2 centimeter, 3 centimeter change, it's going to be able to see that change. Okay, it's going to be able to detect that change. Trees are a little different, and you have a picture of a tree here because ICESat-2, because it uses lasers, it can measure the height of trees. So what happens with ICESat-2? We fire off laser pulses. We fire off 10,000 laser pulses per second from the satellite. They travel to the Earth, and they bounce off objects and come back to the satellite. We calculate the time it takes to do that, and we do that repeatedly. And every 91 days, we go back and look and see how that's changed in that same location that it hit 91 days prior to it. So we're able to measure the ice and trees and water and mountains, anything with elevation, buildings, all of that stuff. Now, one of the trivia questions in the post was how many photons are in each laser pulse, and I saw that most of you thought it was about, I think it was like 300 million, I think, but the answer is actually 300 trillion. Now, the crazy thing about that is remember, lasers are light. So light, as it's traveling, even though it's traveling super fast, light gets reflected, refracted, absorbed, scattered by things like clouds and buildings and water, that not all of the photons come back to the satellite. For every laser pulse with those 300 trillion photons, we get only about a dozen. Yes, you heard that right. 12 photons back to the satellite. But with as fast as the photons are firing, that gives us lots and lots of data in a short amount of time anyway. We get about a terabyte of data a day from the ICESat-2 satellite. And the ICESat-2 satellite has actually measured about 400 billion tree heights so far. Despite there being about 3 trillion trees on the planet, we've measured about 400 billion. And even though that sounds like a big number, 400 billion compared to 3 trillion is a huge, huge difference. So that's why we want ICESat-2 in space as long as possible, so we'll be able to measure this. And there's a way that you can measure it as well, which I'll be getting to in a second with the GLOBE program, which was another one of the poll questions at the beginning of the webinar. I should also mention here that lasers, the scientific term that we use is LiDAR. Okay, if you didn't know that, it's light detection and ranging. So if you hear me say LiDAR versus lasers, I'm talking about the same thing. Okay. All right. So now I'm going to show you a quick video here. This is kind of an overarching one of ICESat-2, kind of explaining why it's up there and what it's measuring.
From satellite data, we have a very good handle of how our Earth looks like. We can see oceans, we can see the sea ice, we can see our forest. What is much, much harder to measure is how high things are on a global scale, almost impossible.
ICESat-2 adds the third dimension, the elevation. Repeating measurements from ICESat-2 will allow us to measure changes in the ice sheets or in the ocean or in land.
ICESat-2 is designed to measure the changes that are going on in the cryosphere, in the polar regions.
All the change is at the edges. Those are the steeply sloping parts of the glacier that interact with the ocean, and that's where all the action is. That's where all the mass is being lost.
In order to estimate the mass changes, we need to know the height of things. The mission ICESat-2 carries a single instrument. It's called ATLAS, the Advanced Topographic Laser Altimeter System.
ATLAS sends out small pulses of laser light 10,000 times a second. And by measuring precisely how long it takes that light to go from the spacecraft down to the Earth and back up to the spacecraft, allows us to figure out what the height of the surface is beneath ICESat-2.
We need to measure the time of flight of a single photon or a single laser pulse with a precision of a billionth of a second.
NASA engineers had to come up with entirely new ways of measuring time very precisely.
A billionth of a second translates to an elevation change precision of just a few centimeters. Climate change is amplified in the polar regions. ICESat-2 is designed to measure those areas and will help us to understand what's going on with our planet.
So as you saw on there, of course, since it's ICESat-2, as I mentioned earlier, our primary science objectives with the mission is looking at the ice sheets and the sea ice and how it's melting. But because it's a laser altimeter in space, an altimeter, an instrument that measures, height and elevation, all that stuff, it can measure other things. So that's why it's measuring trees. That's why it's measuring buildings and oceans and different bodies of water, and anything that has elevation. One thing that's really cool, like not well-known fact is that we were able to measure, and we still can. We've actually measured the height of penguin colonies in Antarctica. So very cool to be able to see that. ICESat-2 doesn't know that they're penguin colonies, so we have to talk to other satellites. You saw earlier all the satellites. So we have the Landsat series of satellites, and in space right now is Landsat 7, 8, and 9. Well, we talked to the Landsat folks, say, hey, we got these weird bumps, these weird elevation bumps in Antarctica at this time, but we know it's not a geographic feature because we know what the terrain looks like in Antarctica because it's been mapped out so well in a lot of the locations. And they went and they checked it out, and they said, yeah, you're looking at penguin colonies. So, the penguin colonies are so big, and they stay there in an area, a lot of the winter in the same location that ICESat-2 is actually able to pick it up. So very cool. So, the laser pulses, must have bounced off the penguins' heads at some point. So no harm for the penguins because this laser is firing from over 300 miles above the Earth. So it's basically what happens is the light is strong when it leaves the satellite, but as it's traveling down to the Earth, the light basically loses, but it goes away, but the energy is still there. And when the photon hits the ground, the energy basically returns the height in an area of a 13-meter diameter footprint. So anything that falls within that 13-meter diameter footprint is the height we're going to receive from ICESat-2. What you're looking at here is a couple cool little data sets from visual data sets from ICESat-2. This is showing you, the left side is showing you the Arctic and the rate of ice change per year. And you can see meters per year. You can see the different colors here, that there's some loss and big loss in some places, some average losses. But then you look over here on the right side, you see Antarctica, and you can see around the ice sheets around there, and that wing out there, that West Antarctic ice sheet that you see, that's where we see it's melting pretty quickly. There's actually a glacier on the West Antarctic ice sheet called the Pine Island Glacier, and for years, and I remember a colleague scientist, Dr. Robert Binchadler, telling me, he's since retired, he's an emeritus at NASA, but he is a cryospheric scientist. He's been to Antarctica and Greenland numerous times. He actually has things like the Binchadler ice stream named after him. But when he was studying the Pine Island Glacier 15, 18 years ago, it was melting at a foot an hour back then. So it's still, on a path to melting that quickly. I'm not sure. I don't know I haven't heard any studies being done directly at that location lately. So, but I'm sure it hasn't slowed down much at all. So, we don't like at NASA, we don't like to be the doomsday scenario people, but some of the data that a lot of the data that we are getting back from the satellites is pretty alarming, and it definitely requires lots of looks at in order to figure out what's going on. That's why we have these satellites in space. So you heard earlier about ICESat-2 from the two voices that you heard earlier. Torsten Marcus, he is the Cryospheric Science Program Manager, and that's headquarters. He was once the ICESat-2 project scientist. And you saw Tom Newman's name there. He's a project scientist for the mission now, but he also does some management as well on the side. So as kind of his main career at NASA, he does a lot of management in the science mission directorate there. So I'm going to show you this video because you heard about the precision of ICESat-2 and how precise it has to be in order to get these measurements and get them as accurate as possible, so we can use them to help us understand what's going on. This is an engineer, Phil Lors. He is a deputy systems engineer for ICESat-2 when it was being built. So he was one of the ones who we went to and said, hey, we need the satellites to do this. We need ICESat-2 to do this. We need to fire off this many photons, but we need it to be this precise. And he's going to explain it to you here.
The ATLAS instrument on the ICESat-2 satellite measures elevation by timing the flight of laser light pulses that leave the satellite, bounce off the surface, and return to ATLAS. The speed of light is very fast, and so a regular stopwatch would give us too wide a range of time, a big margin of error. The timing has to be ultra precise, less than 1/billionth of a second, in order to measure the height of the surface within just a few centimeters.
I'm Phil Lors. I'm Deputy Instrument System Engineer on the ATLAS instrument on the ICESat-2 mission. Calculating the elevation of the ice is all about time of flight. It's time of flight of the photon from the laser down to the surface of the ice and back. So what we are doing is creating time tags of the transmit when the laser fires and time tags of the receipt of the photon. So it all starts with the transmitter. When the laser fires, it puts out billions and billions of photons. We pick off a little bit of that and we send it to a detector and we produce a start pulse. And that is the start of our timing system. The spacecraft sends us a position and attitude message every second that tells us where we are in the orbit. From that, we calculate where we think the spots are on the ground. We have a rough database of the whole Earth with elevation as it travels up and down mountains and down into valleys and over ice sheets. For each spot, we calculate where we think the surface is, and we open up a range window. For every photon that's received in that range window, we produce a time tag. Now, the sun produces a lot of green photons too, many more than our laser does. So our laser produces billions and billions of photons with every shot. If you add the noise in there, you won't be able to tell the sun's photons from the laser photons. So if you just took one shot, the one laser photon would be lost in the noise. But if you take 200 shots, now finally you have enough surface signal coming out of the noise that flight software on board can pick out this is noise and this is the signal from the surface. Once we downlink the photon time tags from the receiver and the transmitter, and we have the range windows, you put those all together, you have the transmit time tags, you have the time until the range window opened, you have the receive time tags in the range window. You calculate all that put together, gives you the time of flight of a photon, which ultimately gives you the distance between the spacecraft and the ground. If you know where the spacecraft is, and you know the time of flight, you know the distance to the ground, now you have the elevation of the ice.
Technology that can measure elevation adds a third dimension to how we map our Earth and allows us to study change across the poles and beyond.
So I hope that gave you a little bit of a better understanding of how precise the satellite has to be built in order to get the data that we need from it that makes sense. And with that data, we can create things like you're seeing on the screen now. And these are two of my favorite ones that we've gotten from ICESat-2. The top one you're going to see is off the Bahamas. So this is the ocean water off the Bahamas. You can see there's the coordinates over here and where it's located on the map. But the interesting thing about this one is that you can see that line that's running down through the middle. The really has like blue, the blue photons on the edge, but it has the darker, thicker green line. That's the ocean surface. So the photons were bounced. Some of the photons bounce off the ocean surface and come back to the satellite. So we get basically the height of that ocean surface. But what you're seeing underneath there, you're seeing that terrain under there. That is bathymetry. So that's actually the ocean floor. So in the Bahamas here, where this was measured, the water was extremely clear, pretty shallow, and pretty still. So the satellite photons were able to penetrate through the ocean surface, travel down to the ocean floor in this location, and then come back to the satellite. On the bottom here, you see this is Sequoia National Park. If you've ever been to Sequoia it's basically Central California, you can, you'll see those massive trees, like the General Sherman tree or the General Grant tree out there. So what's really cool about this is this is showing you the terrain that ICESat-2 has mapped. You can see the mountains, you can see some of the valleys, and some of the look like deep ravines here as well. But what you're really looking at, what I want you to look at, are those green spikes that are on top of the mountains that have the little yellow dots. Once again, those yellow dots are showing where the photons are. But those spikes are the trees. So they kind of look like trees, but they're actually showing you it's basically a collection of millions of photons, that have bounced off these trees in order to give us a return height measurement. So this is two of my favorite ones that we've gotten from ICESat-2. We've gotten a lot of really cool places. A quick story is that one time one of the scientists for ICESat-2 put a challenge out to the folks on the ICESat-2 team and said, hey, go and look at the data and see what some of the coolest and strangest or strangest things that ICESat-2 has been able to measure. And my colleague, Dr. Kelly Brunt, she found that ICESat-2 actually measured the height of a water park in Germany that was built in basically the world's largest airplane hangar. And we could figure it out because it has a dome on top of it. So we were able to see this massive dome and we knew that it was the hangar. But then ICESat-2 flew over it during the day when the dome was opened, and it was able to measure the height of things inside the water park, like the slides and the water in the wave pool and some of the palm trees, and even, I believe, some of the deck chairs that were at the beach area in the water park. So very interesting. But yeah, these are some of the coolest ones that we have, that really showing you that, yes, we're measuring ice with ICESat-2, but we can actually get some of this really cool stuff as well that helps us understand, what the ocean floor looks like, what the sea surface height is, what the mountain and the terrains look like, in that third dimension. So with all that said, with ICESat-2, there's a way that we have designed with what's called the GLOBE program, which is a NASA-funded program, and it's also supported by NOAA, NSF, National Science Foundation, and the U.S. State Department. And what it is the GLOBE program came out in 1995. It was actually a product of Al Gore at the time. In 1994, it was announced. It started on Earth Day, April 22nd, 1995, and it's been continuing since then. And it's a program for students, teachers, citizen scientists, and researchers to work together to understand local environments so they can see the big picture of what's happening across the planet. Now, the GLOBE program currently is in 127 countries, okay? And there's literally over 250 million measurements in the database from the GLOBE program. And these measurements are kind of like I mentioned with the Earth observing satellites, but these are ground-based observations of everything from air temperature to surface temperature to soil moisture to clouds, cloud observations to tree height, biometry tree height to water chemistry, pH, all these different things, alkalinity, all this water chemistry as well. So the GLOBE program is a way for the students and teachers to go out and take observations in the local environment. Now, that was, traditionally they did it using lots of instruments, of course, lots of, to take all these measurements, everything from soil moisture probes to, using soil drying ovens to figure out soil moisture and all that. But we came out with something called the GLOBE Observer on Earth Day in 2016. We started off basically creating this app so you could easily take observations around you by just using your cell phone or a tablet. And we started off in 2016 by releasing the Clouds tool, where you could take cloud observations. Then 2017, we released the Mosquito Habitat Mapper, where you can identify potential mosquito habitats and mosquito larvae to then eradicate those. So we could figure out where these mosquitoes were. And this is a huge part of the science that is being done with students in areas like Thailand and the Philippines and parts of Africa, where we see these vector-borne diseases out there from these really nasty mosquitoes. So this is a way to, you can do this, observe these, where these mosquito habitats are, but then also eradicate these as well. Okay, so we don't want these mosquito-borne diseases around, these vector-borne diseases around. And then in 2018, we released the land cover tool, which aligns to like what the Landsat series of satellites measures. We're looking at how the land is changing over time. And then in 2019, we released 2019, we released the trees tool. And that's where I come in, because I'm also the GLOBE Observers, the NASA GLOBE Observers tree science lead. So because I work on the ICESat-2 mission and the GLOBE program, it fit in well from what I do with the mission and what GLOBE does. So with your phone, you're able to use what's called the internal magnetometer of your phone to measure the angles from your eye level to the base of the tree, to the top of the tree. And you can walk to the tree counting your steps. And that gives you that trigonometry, the numbers in those trigonometric equations that you need to form that triangle between looking at the base of the tree, looking at the top of the tree, and walking to the base of the tree. And then what that's going to give you, that height of the tree. Okay. So we build all the trigonometry into the phone, and we have people from all over the world using this information now. So with tree height, you think it's such a simple observation, right? It seems pretty simple. I mean, you look outside and you see, there's trees probably around your house, there's around, neighborhoods and, where you travel, but you don't think about, you might say, oh, that tree looks tall or that tree looks small, but tree height really helps us understand things. It's actually an indicator of climate change, tree height. It's really a really good marker of us understanding how our climate is being affected by multiple things, especially carbon. Okay, because through the process of photosynthesis, trees pull in carbon dioxide from the atmosphere and convert a lot of it into the oxygen we breathe. But also the trees store that carbon dioxide. That's how the trees grow, right? I mean, they use the sun's energy, they get water and food, nutrients from the soil, but they also store a lot of that carbon, what's called carbon sequestration. And looking at that, the taller a tree is, the more carbon it has pulled out of the atmosphere. Okay. And then, got that pollutant out of the atmosphere. And so tree height is one of the most widely used indicators of an ecosystem's ability to grow trees. It also helps you track the growth of trees over time. And in the science world, getting a little more sciencey, okay, and that's the worst, very sciencey, very mathy as well. But we really look at it to understand the biomass of an area and how much carbon is being pulled out of the atmosphere and either taken in from or released into the atmosphere. And then we have these satellites like ICESat-2. And I say satellites, we actually have an instrument on the International Space Station called JEDI. It's called the Global Ecosystems Dynamics Investigation. And it's an instrument that measures just the tree height in basically the mid-latitudes between 56 degrees north and 56 degrees south latitude. And yes, it is a play on the Jedi, JEDI from Star Wars, because it's Jedi, though, GEDI, but the tagline, and I'm going to warn you here, it's a little corny. The tagline is, "May the forests be with you." So if you're a Star Wars fan, you get it. Well, actually, if you're not a Star Wars fan, I'm sure you get it. Okay. I'm not a big Star Wars fan. My 16-year-old son is a huge Star Wars fan. I'm more of a Star Trek fan. So, but I digress. So as I mentioned earlier, that there are over 3 trillion trees on the planet and approximately 78,000 tree species. Now, as I mentioned, ICESat-2 has measured hundreds of billions of tree heights. That's not close to 3 trillion. But we also have lots and lots of measurements from the ground, because ICESat-2 can't see every tree, nor will it ever measure every tree on the planet. Think of it this way, too. You have a forested area where you have these really tall trees. You're inevitably going to have a lot of smaller trees growing underneath, right? Well, ICESat-2, the lasers are going to bounce off the highest canopy portion of the forest and then bounce back to the satellite. Some may get through if they get past the leaf or between like a little break in the leaves or the foliage there on the trees and be able to hit a smaller tree. But that's where the ground-based observations with the Globe Observer program, come into effect. So what you're looking at here is you're looking at all the tree height observations that have come in through the Globe program, through the Globe Observer. And top left, you're looking at the United States. You can see the East Coast is pretty slammed with lots of amazing tree height observations. West Coast as well. The Midwest and out on the plains, not that much. There's a lot of open space there, so we need to fill that in a little bit. The map on the bottom, what you're looking at the entire globe, and what you're seeing here is approximately over 112,000 tree height observations from over 33,000 global locations through the Globe Observer. So a combination of tree heights from ICESat-2, from the JEDI mission that I just mentioned, and the Globe program, we have a great amount of data in the database for researchers, student researchers, all the way through professional researchers to use in their research projects. Now, getting a little more specific, okay, since we are talking about Mount Washington a little bit, I went and I grabbed some numbers for Globe, New Hampshire, and we need more, okay? Not blaming anyone, okay, but we could use more data. We have in the history, these are from since 2019 when we released the Globe Observer. These are folks and schools that have used the Globe Observer to submit the tree height data. But we have 190 tree height observations in 89 New Hampshire locations. You can see a list. You may be familiar with some things on that list. The top one that says New Hampshire citizen scientists, those are individuals. And we don't identify them by name in the database due to privacy, and we're a federal government agency, so we don't do that. But you can see here we have a bunch of different schools listed here, and some centers like the Leitzel Center, but a lot of schools here, which is really cool to see. So I just want to show you that one. In the map you can see on the left of New Hampshire. Okay, so scientists, we use your data. Okay, there's lots of data coming in, and what you're looking at here is this is a comparison. What I've done, as a scientist, what I've done here is to I went and I found that ICESat-2 dropped a laser photon. I live in Salisbury, Maryland. Okay, it's on the eastern shore of Maryland on the Delmarva Peninsula. If you've ever been to areas like Ocean City, Maryland, I'm about 35 miles away from Ocean City, Maryland. Okay, but it dropped a photon on the ground. So I went out and took observations of it, and I did comparisons between what I got with a globe observer in tree height and what ICESat-2 got. I got 18.93 meters as my average tree height for all the trees that I measured in the area where the photon hit. Remember, it's a 13-meter diameter footprint. So I measured the 13 meters, and I measured as many of the trees as I could in that area with the globe observer. ICESat-2 measured it at 19.66 meters, so super close. Okay, pretty close, pretty darn close. Now I'm going to show you a couple other examples here, and then we'll finish. We'll wrap up and then do some question and answers. But I wanted, and then I'll show you a little bit. I have a little example here for Mount Washington, and I can show you. But this is an example of where I work at the NASA Wallace Flight Facility in Virginia. It's also on Delmarva Peninsula on the eastern shore of Virginia, about an hour south of Salisbury, Maryland. But you're seeing these ICESat-2 orbits, these photons that are rolling through here. And the ones on the left side is what I want you to focus on, with the green and the orange. The green one you can see here dropped right here. Right below it where it says Wallace Flight Facility, that's where my office is in that building there. That's actually one of two hangars on base. You can see the runway kind of off to the right there, off to the east. But that's where the photon dropped. So I went out. Well, I actually found out what ICESat-2 measured it at. It measured out these average trees. And I went out and I found that there were about 5 trees in that 13-meter diameter footprint where it landed. It landed in kind of a little opening in this forested area right here, just near the main gate. But ICESat-2 got a 22.08 meters. So I went out and measured these 5 trees, and I got an average of 23.90 meters. And this is something anybody can do, because once you figure out how to use a globe observer trees tool, it takes only about 30 seconds to a minute to actually take an observation. Okay. I should also mention that when you do an observation, if you happen to have a tape measure with you, you can also do the tree circumference measurement as well at breast height, so about 4.5 to 5 feet above the ground level. So you can do that as well, and that also helps the scientists figure out the carbon that the tree has pulled in from the atmosphere. So I got 23.90 meters. ICESat-2 22.08 meters. And one other one I like to show is that ICESat-2 hit this location also in Salisbury, and I show this because. And I did this because I gave a presentation to a group of senior citizens from Salisbury University, some alumni, in that building that you see in the middle. But the ICESat-2 photon landed just on 2 trees. It looked just the edge of that photon hit these 2 trees. So I went out and I measured them, and ICESat-2, of course, measured it. ICESat-2 was able to measure this average tree height at 4.13 meters, so super small. Okay. I measured it, and what you'll notice here is I measured it basically 3 years later, because I didn't know ICESat-2 measured there, and I didn't have any reason to go to that location to see if ICESat-2 measured. But since I was giving a talk there, I was going to try to find out if ICESat-2 actually measured something, and it did right outside the door. Well, the first tree I measured, 5.73 meters. Second tree I measured, 6.23 meters. That gives me an average height of 5.98 meters. And ICESat-2 measured at 4.13 meters, and that's a 1.85 meter difference. And what's cool about that is that we can probably figure out that growth was from the 3 years since ICESat-2 measured it to when I measured it. So about 1.85 meters in tree growth at the time, because as you'll see, I measured it kind of close in the year to each other. One was in July 28th. Well, ICESat-2 measured it July 28th of 2020. I measured it August 18th of 2023. So that's another example of what you can do. So, I want to show this last one here before we go take any questions here. But this is just an example of what you can do. And this is just these are laser photons that ran straight through, as you can see here, next to the Mount Washington Observatory. And I have the latitude and longitude there. And I hope you can explore this at some point. There's a long website here at the bottom, and it'll be, I guess, in the recording. But this open altimetry is a way that we can go and plug in any latitude and longitude to see if the ICESat-2 mission has measured in that area, has photons have hit that area. So with a globe observer, every time you measure a tree and you submit that to the database, that tree is geolocated. You will get an exact latitude and longitude for that tree. So then you can go into the open altimetry program, plug in that latitude and longitude. It'll center a global map at that location. And when you zoom in, you will be able to see if ICESat-2 measured that location or those trees that you just measured. And what you're seeing here is all these dots here. These are these photons once again. And on the right side, when you do it on open altimetry, it brings up two graphs. One is showing the ground elevation, okay? And that's that line that looks like a mountain, like a hill, right? And you're seeing the individual photons. Then on the bottom, it's aligning any of those photons to when those photons measured trees. And then you can scroll over any of those photons and it'll tell you the exact latitude. You can see how precise that is, the latitude, the longitude, what ICESat-2 says the canopy height is, okay? And you get that just amazing information, just from that. And, I like for people, for you guys to explore that at some point. And if we have time later on, we can do this. But I really want to get to the question and answer session since I'm kind of like 3 minutes over. It's longer than I wanted to talk. But I'm going to come back. I'm going to stop sharing and come back to the main room.
All right, awesome. Well, thank you, Brian, for sharing your expertise here. I loved this presentation. When I was in college, I was studying climate sciences with an interest in cryosphere studies. So we were all very excited when ICESat-2 launched, and it's really cool to see the data, especially for my personal interest, related to the stability of the West Antarctic ice sheet. That was awesome to see.
I should mention that we're about to fire off the 2 trillionth laser shot towards the end of this year. So
wow,
that's a lot of photons being fired. 2 trillion laser shots, 300 trillion photons per laser shot. It's a big number.
That's fantastic. Well,
Yeah.
Congratulations on that. That's awesome. All right. So before we get into the Q&A tonight, I would like to preface how at the beginning of this presentation, we had a little bit of a technical hiccup, always fun, with going live on Facebook. So we're not live right now. However, this will be uploaded to Facebook shortly after this presentation. And if we don't get to your question today, feel free to put that as a comment on Facebook once it's uploaded, and we'll get to it as soon as we can. All right, awesome. So starting off with some questions tonight. So first, going back to GLOBE, is the GLOBE data available for students to use? And if so, what kinds of data are available?
Yes, absolutely. Every single point of data on the GLOBE website, on the GLOBE database, is available for anybody. And the URL is pretty easy. It's just www.globe.gov. And there's different ways to look at the data. You can look at a visualization map. And what that is you can choose if you want to look at tree heights or air temperature or surface temperature, any of the 50 different observation protocols, and you can look at it on a map. For instance, like the map I showed you earlier, if you click on one of those tree pictures, you'll get the picture, but then it'll also tell you exactly where that tree was, how tall it was, and when the observation was taken. And you can do that with all the data is all time stamped. So yeah. So yeah, so you can find anything. There's like some historic measurements out there where there were some protocols that have been since retired, like the migration patterns of the ruby-throated hummingbird and things like that. So things that that didn't get a lot of measurements done. They basically twilighted those and then they got rid of some of those. But you can look at everything from cloud heights and compare those to satellites as well. Soil moisture you can measure. You can do that as well. And compare that to one of NASA's satellites called SMAP, Soil Moisture Active Passive, which I used to be on that team, early on. But yeah, there's lots of different observations you can look at. Like I mentioned earlier, water chemistry, anything in any area, and all that. Like I said, all that data is available. Okay, and we'd love for you to sign up with Globe as either as a teacher or a citizen scientist, but you can access that data anytime. I should also mention that the other two ways are, one's called the advanced data access system, where you can go in and just grab like Excel spreadsheets of the data if you just want that type of data. And then there's something called the API, which a lot of scientists use, which they can grab data from any certain time period and then plug it into whatever program they're using, like Jupyter Notebook or whatever, to analyze that data a little better.
Fantastic. Thank you. All right. We have another question here. What is the source of power to generate the photons on the satellite?
So yeah, that's great. So the satellite, well, source of power is, they're basically really, they're kind of your standard lasers, and it's a combination of there's like iridium batteries, but there's also what was also a trivia question, the 4 solar panels that keep the satellite working as well. So there is a basically a system set up in the satellite, with a particular voltage that it has to stay within a certain ones, or in a certain range. Because if it for instance, that last huge solar activity that we had, where we saw a lot of aurora, over the last, I think it was about a month ago, we saw lots of aurora. We saw crazy aurora borealis here in Maryland, that actually affected the power of the satellite, and the satellite actually had to go in safe mode because basically those solar magnetic forces basically kind of shifted ICESat-2 a little bit, so it had to go in safe mode, so everything had to be retested. So yeah, so it's a combination of, there's multiple power sources on the satellite, the power, the photovoltaic cells of the actual solar panels is what keeps it powered. We were just notified that we have enough power, energy, and fuel on board to run through 2039. But that doesn't mean that the lasers will last that long, because as you know, laser lights eventually die out. The ICESat-1 mission, which was in space from 2003 to 2009, basically we had to decommission it and bring it back down to Earth because the lasers no longer worked. So we weren't getting any observations. They died out after about 6 years. But these look like they're going to last a long time.
All right. So we are getting a little close to our time here today. So I'm just going to do one more question. If we didn't get to yours, or if you think of one later on, like I was saying, we're going to upload this on Facebook, and we're always monitoring the chat section there. So feel free to drop a comment with your question. All right. But the last question of the evening, what are some examples of how this data has been applied to solve environmental issues?
Ooh, we could do a whole presentation on that, but let me try to think of a couple things as well. So let me think something that would be good to. Well, just for instance, we've seen drastic ice melt in basically the southern tip of Greenland. Okay, now I should preface this with, since NASA is a science agency, we don't tell people what to do with the data. We provide the data for people, but we let them know that this is the data that would be most beneficial for your location. So we have folks in the in Greenland who are really worried because they're seeing this sea level rise. I mean, there's areas like around here, a lot of people here from the Northeast, of the Chesapeake Bay. Chesapeake Bay, there's areas in Chesapeake Bay where islands are just subsiding. The bay level is rising. So we're able to see that from ICESat-2 as well. And we can, let the folks know who are, in the environmental groups who are from areas like Tangier Island and Smith Island and, islands in the Chesapeake Bay as well. We also have been working with folks in Amazonia, in the Amazon rainforest area, where ICESat-2 is able to see, of course, the tree heights in the densest forest areas where basically, researchers can't really get to. And we're able to see where could be deforestation or where there could be blight. So we've seen areas where, like massive areas where, the trees have died in areas like in the Amazon, where we can then say, hey, we flew over this with ICESat-2 and we got these great tree heights, and then we've been kept on coming back to the same spot every 91 days, and we're not really seeing anything. What's going on? So then we figure out, we work with the people in those areas saying, hey, we're seeing this, and then we're not seeing this. So this is what you really need to, use that information and take a look at. So, I like that question. It's a loaded question because there's so many different things, whether we're talking about the polar regions or we're talking about, the ice melting in, the Alaskan glaciers. For instance, like the Columbia Glacier, that's one of that's it's a pretty common one. It's a big touristy area as well, for cruise ships to hit. But it's not probably, it is one of the fastest, if not the fastest, melting glacier on the planet. And it's melting super fast right now. And, yes, it's a big tourist attraction, but it has an effect of the people who live in Alaska and around that area. So that's another thing that we're seeing. ICESat-2 has been seeing such a dramatic change in just this Columbia Glacier that we get that information to the folks in Alaska and say, hey, this is what it's doing, take precaution however you need to.
All right, awesome. That was an excellent question. And we're just about actually a little over time now, so we're going to wrap it up. But like I said, watch out for this post on Facebook and feel free to add your question as a comment there. And thank you all for attending and for your excellent questions. And thank you to Brian for an excellent presentation and for sharing your knowledge with us tonight.
Thank you for the invite.
Yes, thank you very much. And again, this is a free program. And if you'd like to support the nonprofit Mount Washington Observatory and our work, we would greatly appreciate if you went to mountwash.org and hit the donate button there. And also earlier on in this presentation, I talked about Seek the Peak. That was one of our poll questions. So we're asking for hikers of all ability levels to join us for our 24th annual Seek the Peak. This is our largest fundraiser, and it's an awesome event, a fantastic hike-a-thon. And we ask these hikers to pick a hike, raise funds for the observatory, and they can earn gear and celebrate at our Après Hike Expo on Saturday, July 20th at the base of Mount Washington. We're going to have live music, great food, drinks, outdoor gear vendors, a rock climbing wall this year, which I'm super excited about, gear raffle, and a lot more. You could sign up as an individual or meet up with some people and hike together or create a team. You can learn more at seekthepeak.org. And also, too, if you enjoyed this program, we will have a survey going out with our follow-up email. And also, if you have any suggestions for any speakers, definitely feel free to let us know. And finally, don't forget to join us for our next Science in the Mountains meeting on Tuesday, July 23rd at 7 p.m. We're going to have Project Drawdown's Managing Director, Elizabeth Bagley, and she'll join us to share all about her organization's work on climate change solutions. All right, fantastic. Well, once again, thank you everybody for joining tonight. It was a pleasure hosting my first Science in the Mountains here. So thank you all. And once again, thank you to Brian, and have a wonderful evening. And for those affected by the heat, stay cool these coming days. All right, take care, everyone.